Hello, here we are once again, and I'm getting a little earlier start on this. This is the lecture for Monday, March 30th, but I'll post it as soon as I have it up. And what do we have here for the announcements? Okay, Physics 105A, video lecture 5 for Monday, March 30th. I'm going to talk about the duration of these lectures. I was hoping to keep them shorter rather than longer. I saw one of them crept up to 50 minutes. Can happen pretty easily. But if I'm around 35 minutes, that would be ideal. I'd like for you guys to be able to take the notes, go back, fill in some more information, leave a lot of space, I'm saying that again, where you can fill in missing stuff, or you can fill in missing calculations, or you can even fill in some other wisdom that you get from elsewhere. For example, recently we had all this talk of the integral theorems. Okay, that's a major topic. You could leave a little room there. I was just sketching how they're pertinent to what we're doing. Good, be that as it may, we're now talking about the central force, and I'm going to review what we did and then take us on into the new topic, which is the effective potential. But just watching this review unfold is actually going to be worthwhile. So just step by step now, we've done all these steps. I can write them all down. We start with Newton's law, of course. We're now in 3 space. And we have a central force. This is what a central force means right here. There's a unit vector, magnitude of that force here, directed towards or away from the center, from the origin. So there's our central force. Immediately, although it took us more than immediately, but we now have the potential energy, and it is of this form right here. Okay, there's your potential energy. So you take that magnitude function and integrate it up to R. And of course, the derivative u prime of r gives you back f of r. Okay, so that's good. From this, and this is equivalent to having conservation of energy. So now we have 1/2 m r dot squared plus u of r. So that r is the magnitude of that vector r equals E. I'll just write equals constant. That's conservation of energy. Then I introduced the angular momentum. Angular momentum. Can't claim that that was especially motivated at this point, but it certainly was true, and we found that the angular momentum r cross m r dot equals L is constant. So we have conservation of angular momentum conserved. Okay. And I didn't say anything about why it's conserved. I just went and did the proof. The reason it's conserved, the proof is so short I can do it again. dl dt is equal to r dot cross mr dot plus r cross mr double dot, which is f of r, which is f of r. Yeah, both of these are parallel, so that's 0 by the definition of the vector product. This one here expresses the fact that the central force can exert no torque. Okay? You can't get a torque out of a central force, because if you're a particle here, and there's the origin, okay, and the force is directed like that, where's the torque? Okay, where's the lever arm? Okay, force is a torque times a lever arm. There is none here. Practically speaking, if this is a ball whirling around on the end of a string, that string can exert no torque. It's flexible. It only has tension. Okay, so that's where that comes from. That's the significance of the angular momentum being conserved. Okay, I'm going to erase this. That's just a little note on the side we could have had last time, but we didn't. And out of this, we get the motion is restricted to a plane. A plane. And you can just look at it like this. This is your XY plane, and your L vector happens to be pointing in Z direction. So since the motion is restricted to a plane, we can use plane polar coordinates. Use plane polar coordinates, and then if this is X and Y, you've got a point out here, R and phi. Okay. So far, so good. Back again, had to write a little note on the board. Okay, so that's where we had gotten to, and then I'm going to erase this now. We had the conservation of energy and the conservation of angular momentum had been written down in plane polar coordinates. So that's what I'll write down next. And this time we'll take off with that. So this was all review, a little extra. Good. Okay, so now conservation laws. In plane polar coordinates, we have 1/2 m r dot squared plus 1/2 m r squared phi dot squared plus u of r equals e. So these are the two from the kinetic energy in plane polar coordinates, potential equals energy, and we have m r squared phi dot equals L. Good. So those were the couple differential equations I left us with last time. And the idea is, I'll just write here, solve to obtain R of t, phi of t, and with both of those, R of phi, or phi of r, which is actually going to be our big goal. Good, so there's the problem, and we have to go about this systematically now. A couple differential equations, first order differential equations. And the way we tackle this is with this next step, that we take the angular momentum, which is proportional to phi dot, so we'll solve for phi dot L over m r squared. Take into energy. Okay, we're going to take that into the energy expression and see what happens. Here's what happens. Phi dot squared, I'm going to have L squared, m squared, r to the fourth. Cancel the m's with the r squareds. Here's what I get. Write it down now, let's go right here. We have 1/2 m r dot squared plus L squared over 2mr squared plus U of R is equal to E. So that's the energy now, and this hasn't changed, so I'll just write phi dot is equal to L over 2mr squared. But now things have been effectively separated. Separated because this is just R dot and R. So we could and this, okay, this is just R dot and R. We could separate variables, do a quadrature, do an integral, and we could get R of t out of this. At least in principle we could, okay? We get R of t out of the first equation, and if R of t is known, then this is a simple integral, you know, direct integration to get phi of t, and then we have our problem, okay? Solved. So that's one way to look at it, and we're going to first concentrate on this. Okay? We're going to concentrate on this one here, and this is where I define what's called the effective potential. Okay? So let U effective of R equal L squared 2mr squared. This is just the definition, plus U of R. Now, this term here, remember, this one came from here. This is part of the original kinetic energy. But right now we're calling it part of a potential energy. Then this expression up here looks like this: 1/2 m R dot squared plus U effective of R is equal to E. Okay, put a box around this important expression, because this is now just a one-dimensional problem. It's the radial equation up here, what this is called. It's a 1 degree of freedom or one-dimensional problem. And we can just analyze it with all the skills we gained doing one-dimensional physics. Okay, so this one-dimensional physics wasn't contrived at all. Here we go. You know, we can separate variables here. We can do a quadrature. We can analyze the potential energy just the way we used to analyze potential energies in the one-dimensional case. The whole thing. Even though this is just a part of an actual two-component problem, you know, two-dimensional problem that lives in the plane. So this is a point that takes people a little, experience shows, takes people a little time to get used to. This came from the kinetic energy, okay? It's not part of the original potential energy. Formally, this expression looks like a one-dimensional problem with a potential energy. And yeah, you can get with a potential energy, that's what I want to say. So what we're going to do next is analyze a couple of these and see what happens here. Just everything we learned before when we were doing conservation of energy, one-dimensional problem, we can apply here. Okay. Periods, oscillations, everything is part of this as well. Okay, so let's leave this up and do the example that I'm looking to do. And that is one of our potential energies we talked about the other day. U of R equals 1/2 K R squared. That was the three-dimensional oscillator. This is something whose properties we already learned about. I had the solution to this thing. It turns out I had the solution on the last exam. That last exam, I think so. So, there were elliptical orbits and what have you. Okay, it was a central force law. Different formalism than we're using now, by the way. Yeah, so here's what we'll do. We can graph this just for the heck of it, but what we really want to graph is the effective potential. So the effective potential here, U effective of R is equal to L squared over 2 R squared plus 1/2 K R squared. So this guy here is just in the way, didn't really need it. Okay. Plus 1/2 K R squared. Yeah, what does this graph look like? Well, we have done things like this before. We have our 1/R squared dependence, and we have our quadratic dependence like this. And if you add those two curves, you're going to get something that goes like so. Now this graph is so important, I could make it bigger, but let's run with what we have. Okay, this is not such a bad size. This is the effective potential, so we can say that this is an energy axis. Energy axis. Okay. This is of course R, and here I'll get rid of these for us. Trace there. And what do we have here? We have a function with a local minimum. I'm going to call it R sub 0. And that local minimum would correspond to a minimal energy, E sub 0, I'm going to call it. And that's the minimum that the energy can take or it can have given a particular value of L. So we got a value of L, conserved quantity, and then the energy can only take on these values here, or is the minimum one it can take on. And I'm going to right now even put in an E sub 1. This happens to be a larger value than the minimum. Let's make this clean. Yeah. So there's our effective potential. I'm going to leave this thing up here. And now we get to analyze this thing. Well, actually, I'll leave this here to be effective. So we're going to analyze this thing. What's the meaning of this R sub 0? So, suppose energy E is equal to E sub 0, referring to my graph and referring to this function right here. Suppose E is equal to E sub 0. Now, you know what? Let's plug in our 1/2 K R squared. Okay, now we're really talking about that particular graph. So what, suppose energy E is equal to E0. Okay, so E here is E0, then we know that R must be R0. And that's the only value R can take on. R must be equal to R0 because we're at that minimum. And R dot must be equal to 0. That is to say, this equals E0. This term can only be 0. Therefore, R dot is 0. That means R0 is equal to constant. Right? The one and only R0. And what is that now? R0 is equal to constant. Well, remember, we still have, should I put this here somewhere? We still have phi dot is, oh, go ahead and fill this in. Phi dot equals L over M R0 squared, which means that phi dot is also constant. And if I want to do this, I can call it omega sub phi. It's a constant. And what does that mean? It means we're talking about uniform circular motion. So this here is the case of uniform circular motion. Completely uniform circular motion. Right? So omega sub phi. All right. So what do we know about uniform circular motion anyway? That's something we've always studied and remembered some stuff about from physics 4A and elsewhere. Yeah, if we have uniform circular motion, then we must have that famous centripetal force, centripetal acceleration expression should be built into here. Okay. And I'm going to make that a homework problem. I could just bang it out here, and it's not hard, but got everything up here, including this. We've got the energy. So I'm gonna have to erase something. Erase something, and I'll redraw it in a moment. Okay, when I have this up here, actually, I'm gonna erase this. I'm gonna erase this. Leave that picture up here. So we're talking about uniform circular motion. So here's our homework problem. Homework. Differentiate. You're going to differentiate U effective. U effective of R. So U effective prime of R0 equals 0, and show that out of that we get U prime of R0 equals M E squared over R0. Okay. And I'll even put the hint in that I could have had here when I just erased this, noting that V is equal to omega sub phi R0. That's just the omega R omega expression for V for uniform circular motion. So yeah, that's just a few lines, but it's a nice thing to have. You leave some space in your notes, knock it out, keep it in your notes as well, but then turn it in on the homework problem just to show me that you did it. Okay, so that's a good problem. What's next is the discussion of the case where E is equal to E1. Case where E is equal to E sub 1 in our graph. Same graph that's still on the board here. So E is equal to E1. And we find, let's see, we're going to have to erase the homework problem. Okay, homework problem, gone. Because we're looking back at 1/2 m r dot squared plus, this time I'm going to write plus U of R. So I won't write the concrete case, the general case here, equals E. So we're talking about E is equal to E1. Then I'm going to dot all the way across here. Then there are many values of R for which this equation can be satisfied. Okay. Because for all the values of R between these 2 points I'm indicating here on the R axis, I'll call one R min and I'll call the other one R max. For all the values between there, this equation has a solution. At the endpoints R min and R max, this effective potential solves it. And again, that means R dot is 0, and those are the turning points. Okay? This is exactly what we did with the one-dimensional motion earlier in the semester. So the case when E is equal to, in our graph, we have now R min less than R less than R max, and R min, comma, R max, or turning points. Turning points of the motion. Good. Just like the one-dimensional analysis, except it's not one-dimensional motion. So we're going to block out this much board to put in my next idea here. So turning point, but it's not one-dimensional motion. So what we have is R is between R min and R max. We still have phi dot is equal to L over M R squared. So you can even see when R is smallest, phi dot is greatest, and when R is greatest, phi dot is smallest. Okay. So let's go ahead and say, where is this motion taking place? It's in the XY plane, so I'll even draw an XY. But it's taking place between two radii. Let's do another try here. Okay. So we're looking in the XY plane. There's R min. There's R max. Okay, you do a better job. Well, there are two circles. This is an annulus. Min, R max. And the motion is going to take place within that annulus. So for example, I'll draw this fat. You could have a trajectory that increases, and then it decreases again. It doesn't even close on itself, and then it increases again, and so on and so forth. Okay? But it'll never go inside of the smaller circle, it'll never go outside of the bigger circle. Yeah, so that's what the solutions to this problem are going to look like. Okay, turning point R max. Yeah, should we turn any of this into another interesting problem? So far so good. Let's see, I'm about to wrap it up for this session here. The turning points, not the effective potential. I'll do one more, I'll set up one more problem now. Okay. So good, we have the general expression right here. And got a nice, interesting homework problem on that. I'm going to give another example. Central force table. This is something that is just a useful discussion, so much so that we have this in the Physics 2A book, and we use it all the way in the graduate classical mechanics as well. Yeah, the idea is you got this table here, you've got a frictionless puck, and it can slide around connected to a string here, and you pull the string through a hole, and you can pull down on it there. Okay. So yeah, you can pull down on this string, and this thing would do all kinds of fun stuff. You release it, bigger, smaller circles, etc. By the way, this is a nice demonstration where you're going to see there's going to be conservation of angular momentum here. Okay, because that string is as flexible as can be. It's not going to be able to exert a torque on this thing. If you pull on the string and the circle gets smaller, the puck's going to have to speed up. Okay, so there's a central force table, and we can call this thing M1 and this thing M2. And then, what's the potential energy? What's the potential energy of this system? Well, this is a flat tabletop, so the potential energy just depends on positive direction there. So U of R is equal to M2GR. M2GR, because as this mass varies up and down, this R increases correspondingly. So if I increase R, this thing goes up the same way. So M2GR U effective is L squared over 2MR squared plus M2GR. And again, L is a constant here, constant angular momentum. The energy would be this plus this equals that, would be the energy. So, just to ball rolling on this one, how about we just find R sub 0. In other words, find the circular orbits given this, and it'll be the minimal energy that solves this equation. You could also graph this thing, but I'll graph it for you. That's the potential. It's going to come in like this and then go up linearly. Good, so find R sub 0. We'll leave it at that. Okay, we'll pick up with this one probably later. In fact, we'll see this one next semester again in the project mechanics. But here's a good time to talk about it as well. It's a central force problem. It's not the central force problem, as we're going to see next time. My next topic here, after I make sure I've done enough here on this stuff, the next one is going to be to take a brief excursion to the two-body problem, so we can come back to the one-body version of the two-body problem using Newtonian gravity. Okay, to talk about Newtonian gravity, we have to have two bodies that are attracting each other. Good, so we're headed there. This is enough for today. All right, that'll do it.